God said, "Let there be light," and there was light. But what is light? So today we shall know how a few important scientific developments led to the discovery of the true nature of light, and we will also do a few fun activities. So let's begin. In ancient Greece, philosophers gave different theories on how we see. For example, in the 5th century BC, Democritus suggested the eidolon theory. Phantom images or replicas come out from objects and enter our eyes. Hence, we can see them. However, Socrates and Plato said that images come out from our eyes and fall on an object, so we can see the object. Around 500 BCE, Pythagoras developed a theory of vision much simpler than that of Plato. He said light is emitted from luminous bodies, can suffer reflections, and causes the sensation of sight when it enters the eyes. However, Aristotle disagreed with both these theories of emission and intromission. He believed the light was some kind of disturbance in the air, one of his 4 elements that composed matter. As Europe entered the Renaissance period, the focus on light shifted to France, Holland, and England. Yet, the debate continued. The corpuscular theory of light was set forth by René Descartes, the same person who had developed Cartesian coordinates, and later pushed by Sir Isaac Newton, who argued that the geometrical nature of reflection and refraction could only be explained by a stream of infinitely small, perfectly rigid and elastic, very fast moving particles with negligible mass and having different sizes and colors. But other optical phenomena like diffraction, interference, and polarization could not be explained later. The cause was said to be mechanical repulsion in case of reflection and mechanical attraction in refraction. Accordingly, the theory suggested that light would travel faster in water than in air. At about the same time, Christian Huygens floated the idea that light travels in the form of waves and that each point on an advancing wave front behaves as a point source for another wave. The wave theory could successfully explain the laws of reflection and refraction, linear and spherical propagation of light, and predicted that light would travel slower in water than in air. However, Huygens failed to explain diffraction. Diffraction refers to various phenomena that occur when a wave encounters an obstacle or opening. It is defined as the bending of waves around the corners of an obstacle or through an aperture into the region of geometrical shadow of the obstacle or aperture. Huygens believed that since all waves need a medium to propagate, so an all-pervading luminiferous ether carried the light waves and vibrated in the same direction as light. Thus he thought of light waves as longitudinal waves. Hence, the theory could not explain the phenomenon of polarization. Meanwhile, Olaus Romer had already measured the approximate speed of light using timings from Io's eclipse on Jupiter at different times in a year, and later James Bradley refined the value by discovering and then measuring stellar aberration. And even later, Armand Fizeau experimentally derived the speed of light using rotating wheels, and then Leon Foucault improved using rotating mirrors. But let's settle here. Hippolyte Fizeau measured light speed in water and proved that it was slower than in air, a direct validation of the wave theory's prediction. In the next century, Thomas Young's double-slit experiment concluded that Huygens was correct, as the phenomenon of interference could be explained by the wave theory of light and could not be explained by the corpuscular theory. And so, diffraction could also now be explained by the wave theory. At those points where the two waves have the same phase intensity, that is amplitude is maximum, and where the phases are out of sync, they cancel each other, and so the intensity decreases. Soon afterwards, Augustin Jean Fresnel experimented with two thin prisms joined together at their bases, that is a biprism, and passed light of single wavelength, that is monochromatic light, through it, and could measure the wavelength, assuming and then proving experimentally that light consisted of transverse sinusoidal waves. He could explain all optical phenomena, including polarization, with this theory. The plane of a sinusoidal wave can have different orientations with respect to the axis of propagation. Hello again. So, let us see more fun, amazing optical phenomena using very simple items. Okay? So, firstly, let's check what happens if we take an old compact disc, that is an old CD, and if we shine light on it, what will happen? See what happens. Can you see? You can see all the 7 colors of our rainbow, all the Vibgyor colors in our spectrum of visible light. Why is that so? This is because there are circular etchings on this old compact disc, and when light shines on it, it causes diffraction grating. So, because of diffraction, we can see beautiful 7 colors in our spectrum. So, this is a simple and easy phenomenon. You can just check by using a CD if you have one, right? This is diffraction. Now, let us check another amazing thing by using a biprism. Why biprism? This is a normal prism, single prism. Why is she saying biprism? Because this, if you draw a perpendicular here, then there are 2 triangles. So, if we, make a cross section, there are 2 prisms. So, we have joined them together. So, it is a biprism. So, there are 2 prisms. Now, here, let us make the room dark and see what happens if we put a monochromatic light, that is laser light, okay, where all the wavelengths are equal. So, let us check. First we will place the prism in this way so that the edge is on our direction, okay, and we will see what happens on that wall. So now let us make the room dark. First, let us apply it on any one of the surface. We can see the light is going that side, right? Now if we come slowly, do you see that? Do you see what that is happening? This is interference. This is what Fresnel did. Can you see? It is such an amazing phenomenon of interference using a simple biprism. So you can always try this at your house. And again, if you move from the edge, nothing is happening. Right at the edge, this amazing phenomena happens. Of course, I'm scared of this darkness, but this amazing, interesting phenomenon, it makes me happy, So, I hope you like this. Let us move on to the next part of the video. In the 1800s, another radical development was happening. Hans Christian Ørsted, Michael Faraday, Andre Marie Ampere, and others had intertwined electricity and magnetism. Electromagnetism was established, and later James Clerk Maxwell introduced mathematics into it. Well, too complicated. Maybe I'll understand this after a few years. It was thus established that electromagnetic fields can travel as transverse sinusoidal waves at the speed of light, and these waves show all the properties of light, thus proving that light was a form of electromagnetic wave. Mathematically amalgamating three seemingly unrelated phenomena, electricity, magnetism, and optics. What an amazing fusion! However, the ether medium concept prevailed. So far, so good. Classical physics was supposed to have reached its pinnacle, but physics received a double jolt that ultimately heralded the era of modern physics, a new way to understand and explain nature. In 1887, American physicists Albert Michelson and Edward Morley carried out their landmark experiment to detect this ether. By comparing speed of light in different directions, and the result was negative, which proved that ether simply did not exist. And then Heinrich Hertz discovered electromagnetic waves, the existence of which was predicted by Maxwell. A step-up transformer, as you can see, produced a high voltage AC current, causing a spark across two pinpoint electrodes in a radiator or antenna coil. This caused action at a distance, that is, another spark in a nearby receiver coil. Then he placed this setup inside a dark chamber and found that the spark gap decreased, that is, the current flowing in the receiver was lower. On placing the setup inside a glass chamber, the gap increased. And when a quartz box was used instead of glass, the spark gap increased further. And finally, when the cathode was irradiated by ultraviolet rays from an arc lamp, the gap was maximum. This suggested that the UV rays were generating electric current. What a great finding! Soon afterwards, Wilhelm Havelock demonstrated that UV rays falling on a zinc plate connected to a battery generated current. He formulated the hypothesis that a conductive plate on which to focus ultraviolet light carries a positive charge because the negative charges, that is electrons, are thrown away with the energy of the lights. Sir Joseph John Thomson then showed that the amount of current varied with the intensity and frequency of the radiation used. The classical wave theory had predicted that the energy of a wave depends on its intensity or amplitude and frequency, both. So, a low frequency red light with sufficient intensity should give the same energy boost as a high frequency blue light with lower amplitude. So, Thomson's findings were consistent with the classical electromagnetic wave theory. Then comes the jolt. Even a much brighter red light could not generate a current, whereas a dimmer UV ray could. Working in a high vacuum by exact measurements, Philip Leonard showed that the number of electrons projected is proportional to the energy carried by the incident light, while their speed, that is to say their kinetic energy, is quite independent of this number and varies only with the wavelength and increases when this diminishes. These facts conflicted with the prevailing wave theory. In the meantime, another problem perplexed physicists: the black body radiation. A black body absorbs all incident radiation, that is, electromagnetic waves falling on it, and reflects none. This is true for radiation of all wavelengths and for all angles of incidence. However, it can emit energy such that the wavelength or frequency of the emitted radiation depends only on its temperature and nothing else. The relation between temperature of a black body and wavelength or frequency of its emitted radiation, as was found out, is shown here in this picture. As you can see, we can clearly see that at any temperature, energy is emitted in all wavelengths, but maximum energy is emitted at a given wavelength where the curve peaks. If we assume stars to be black bodies, then we can indirectly measure their temperatures by seeing the colors of light they emit. See this picture. We can see the temperatures can be determined by using the black body radiation curves. The wavelength where the radiation reached a peak was fixed for a given temperature and was inversely proportional to the temperature. This law was stated by Wilhelm Wien. Using classical physics, Lord Rayleigh and Sir James Jeans showed that the total radiation emitted at any temperature should be inversely proportional to the fourth power of the emitted wavelength. But this law agreed with experimental results only in the low temperature, low energy range, that is for long wavelengths and low frequencies. It deviated at higher frequencies, that is smaller wavelengths. This suggested that at a higher temperature, the black body would emit a huge amount of radiation and lose all of its energy, the so-called ultraviolet catastrophe. So something was wrong somewhere, and the much needed out-of-the-box idea was given by Max Planck, who suggested quite empirically that electromagnetic energy could be emitted only in quantized form. In other words, the energy could only be multiple of an elementary unit. We already knew that matter was not continuous. It was discrete, made up of atoms or subatomic particles. But this idea that energy was also discrete and not continuous was, of course, a radical one indeed. Here we can see an analogy of a ball falling along a step vis-a-vis rolling down an inclined plane. In the latter case, gravitational potential energy is lost continuously, while in the former, the loss is in steps, that is, discrete. But however queer it sounded, its predictions about the black body radiation perfectly matched with the experimental results. Planck's postulate as the packaging or quantization of energy came to be known as laid the foundation for Albert Einstein's theory of photoelectric effect, and physics made a quantum leap in understanding reality at the micro level. Now we will see an interesting application of photoelectric effect. So we will be using a LDR. What is that? a light detecting resistor. So here we have this, and it uses the principle of photoelectric effect. In this resistor, what happens is when light falls, the electrons absorb the photons in the valence band, and so they get excited and they move to the conduction band. So now if you apply an EMF, what will happen? The current will be able to flow very easily and more easily. So this is the application of this photoelectric effect by using a photoresistor. So now let's get started. So the materials required are a 5 volt DC current. Okay, we have the power supply and the breadboard. We need an LED. I have taken a yellow LED. 330 ohm resistor, and of course the photoresistor. Okay, and besides that we also need scissors, tape, wires, light, etc. So let's get started. So we will start with the LED. Okay, and we will connect the anode to the positive terminal. Yes, so we have a wire to connect that. After that, we will take the 330 ohm resistor and connect it to the cathode of the LED. Finally, we will take the photoresistor and again add it to the other end of the 330 ohm resistor. We need to fix all of them firmly so that our circuit can work. Okay. Finally, we will take a black wire, a wire to connect or rather ground the circuit. So now our circuit is ready. We don't need another LED. So let us switch on the power and see what happens. Yes, so as you can see, now the LED is glowing, right? It's glowing. Very good. Now let us use a cardboard piece to block the light from falling on the photoresistor. Let's see what happens. Let me zoom in so that you can see better. Do you see the change? Do you see the change in the LED? Let me show it better, clearer. Do you see? When I am putting the cardboard piece and blocking the light, the LED is becoming dimmer, and when the light is falling on the photoresistor, the LED is glowing. So, photoelectric effect works. Right? Amazing. So, now let's check this photoelectric effect by using a few more types of light. So, now we will use a multimeter, okay, to check the DC current flowing through the LED or rather the circuit when we use different types of light. So first I will switch off the power supply, let the residual charge go. Until then we have this red color filter for us to use when we require red light. So we will use this. Okay, this has a whole basic cardboard piece. Okay, and we also have something special, that is UV rays, UV light. So we will also use this to check what happens when we put it on the photoresistor. Okay, so to measure the amount of current flowing quantitatively, we will use the multimeter. So first let us break the circuit for us to connect the multimeter to the circuit. Okay, we will take out this wire. Okay, now we will connect this photoresistor here and another wire. This should be in the cathode. This should be grounded. Yes. Can you see these two black wires will be connected to the leads of the multimeter. So for that we have some red tape to make it stable. So first we will take one of the leads and connect it to, or rather tape it to this wire. So let's cut a piece of tape. So now we have the setup ready and we will fix the multimeter to DC current. We will fix to about 20 milliamperes. So now you can see the LED is glowing. So now you can see also the amount of current flowing, right? Approximately 1 milliampere. So here we have some flashlight. We will be using it on the photoresistor. Let's see what happens. Okay, it's glowing brighter when we bring the light towards it. Otherwise it's glowing dimly, right? And when we bring light near it, the amount of current has changed, 7 milliamperes. So if we remove this, see, only 1.3 or maximum 1.4. When we bring it again, God, look at this, 7, approximately 7 milliamperes. So this is amazing. Now let's take away the normal light, and as I said, we will use this time flash with red filter. So for that, let us make this way. Okay, and then we will use it to throw that. Before that, let's see, approximately 1 milliampere. Now when we throw the red light on it, maximum 2 or 3, maximum 3 milliamperes, right? So when we bring the red light, 3 milliamperes. When we take it away, 1. Isn't this fun? The actual use of photoelectric effect. You can see it right here. Okay, so now let us also use laser to check what happens. So here we have the laser. So normally it is 1 milliampere. On applying laser, it increases and increases a lot. 5, approximately 6 milliamperes. So increases 6 times. So that is also nice, right? Finally, we will be using the UV ray. So for that, of course, as I showed you, we have this. Okay, so now let's see again. 1 milliampere. See, oh God, 12, no, 13 milliamperes. Do you see the light glowing so well? Again, if I take away the UV, 1, Again UV, 12. No, 13. 13 milliamperes on UV rays. So we can already conclude that light, the photoelectric effect, depends on frequency and not intensity. So you just proved that. We used red light, we got 2 milliamperes. We used UV rays and we got how much? 13 milliamperes. Even though the intensities are the same, the frequency changed it, right? The UV rays frequency are higher than the red light, and so the LED was glowing more, thus resistance was less, thus current was flowing more. So, did you enjoy? I enjoyed very much. A photon is thus a packet of electromagnetic energy with no rest mass, no electric charge, and travels in vacuum at a constant speed of 299,792,458 meters per second. It doesn't get disturbed in an electric or magnetic field. Its energy is proportional to its frequency. Intensity of a beam of light depends upon the number of photons passing through an area. An electron can absorb or emit a photon. This means that only integer multiples of a unit energy can be absorbed or emitted. Thus, a photon is a unit of electromagnetic energy. When an electron absorbs a photon, it rises to a higher or excited state. Now, when it emits a photon, it again reverts back to the initial state. Thus, energy levels of electron orbitals are also quantized. So, if an electron absorbs a photon with sufficient energy, and that means a sufficiently high frequency, it will be raised to such an orbital where it is almost free from the electromagnetic force by the parent nucleus. That is, it will be available for drifting if a potential difference is applied. This frequency of a photon, which can set an electron, so to say, is called the threshold frequency. Any photon below this frequency will not be able to set free an electron, and the energy needed to break the electron's bond with its parent nucleus is called work function. So, part of the photon's energy will set the electron free, and the rest will impart a kinetic energy to the electron. Thus, no matter how bright a red light we may shine on a piece of metal, no current will flow. But even a dim ultraviolet radiation will exhibit the photoelectric effect. Einstein received the Nobel Prize for this work in 1921 for his works on photoelectric effect, 2 years after Max Planck received his, for the discovery of energy quanta. So much for theories and experiments. But did our life change for any better? Well, we have solar panels generating electricity. Last year, I saw a huge array of such panels in Jabalpur in Madhya Pradesh. We also have solar heaters, night vision cameras, burglar alarms, automatic door movements. We all owe these to the photoelectric effect. Thank you for watching. I hope you enjoyed this video very much. Hope to meet you soon. Bye.